Hey everybody, in this video we're going to find the radius of convergence for each of the following series. Alright, so to find the radius of convergence, when you read those words, we're going to be using the ratio test. The ratio test will give us the radius of convergence. Before we apply the ratio test, it might be helpful to kind of expand this power series. So allowing n to be 0 to start us off, 0 factorial times x to the 0 power. We know that's just going to be 1. So what I'm going to do is just generate a few terms of this power series. When n is 1, we have 1 factorial times x to the first power. When n equals 2, etc. It's just good to see the structure of the power series. And at this point I'm just going to say plus dot 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 plus, and then repeat the term here. And continue with the plus dot dot dot, indicating it continues. Alright, something else to pay attention to is what is the center of this power series? Well, we can quickly see from this term right here that the center is x equals 0. Alright, and so in order for us to find the radius of convergence, we're going to apply the ratio test. So remembering again that the radius of convergence means how far off horizontally, how far off the center to the left and to the right of x equals 0 would this function, I guess you can kind of consider it by saying, well, how does it grow? Does it just, as you keep adding another term, etc., when you graph them, does it only intersect at the center, or as you add another term, etc., and graph, are you expanding to the left and to the right and kind of carving out another function? All right, so the center is important. The expansion isn't so much important for the topic of finding the radius of convergence, but what you could do is after you find the radius of convergence, you can go back in and you could graph y1, y2 would be to pick up 2 terms, y3 would be to graph these 3 terms, y4, etc., and just kind of watch the progression of those overlaying on top of each other to see if, as you add more terms, the function does grow or not. Alright, so let's apply the ratio test. So when you read the words, find the radius of convergence, just know you want to go straight to the ratio test. Alright, and we learned this in a previous lesson, that it's the limit of the quotient of 2 consecutive terms. Alright, and studying this term right here, every n gets replaced with n plus 1. Alright, and then we're going to divide that by the previous term, which is just n factorial x to the n. And just a real quick observation, when we applied the ratio test previous to now, if you might remember, we didn't have a power function, we didn't have any variables x in there, all we had was the n variable, I guess, which represents just a particular number. So that's what's noticeably different. We have an x in here because we have a power series. Alright, so how we handle that will be determined here in our next few steps. Alright, let's simplify it. And for this factorial in the numerator, what we might want to do is pull out an n plus 1 and then multiply it by n factorial. And if you wanted to, you could separate here and have x to the n times x to the first, making our canceling work easier. A little bit of cleanup here. The n factorials cancel. X raised to the n power cancels. And we're left with quantity n plus 1 times x to the first power, or just x. Okay, and again, this is different because now we have a variable x in here, because we have a power series, not a series of constants. Okay, so these next few steps are going to be a little different. Okay, what happens is the limit is only dependent upon n, so this x in here can be pulled out in front of this limit statement. And when I pull it out, I have to keep in mind that it could be positive or negative. So as I pull it out, this is what we'll do. We'll pull it out with an absolute value around it. All right, so the limit doesn't depend upon the variable x, it just depends upon n, because that's what we're approaching here, as n is approaching infinity. So pull the x out in front, leaving the rest of the limit statement in terms of n only. Okay, and now we can work on finding this limit answer right here. Well, as n goes to infinity, we can see that the limit goes to infinity. So what we end up with is the absolute value of x times infinity. Well, that product is just going to be infinity. All right, now in our memory, we go back to the ratio test, and we remember that when we apply the ratio test, if we get an answer of infinity, which is greater than 1, the ratio test tells us that this series, or that series at that point, diverges. Okay, so for us, the power series diverges everywhere except for at the center. Every power series is going to converge at least, at minimum, at its center. And because we applied the ratio test and we ended up with infinity, a number greater than 1, okay, it just tells us that this power series converges only at its center. So I'm going to come down here and say, therefore, stack of 3 dots, by the ratio test, this particular series, the series that we're referring to up here, okay, the series diverges. All right, but to answer the question, to find the radius of convergence, well, I'm not going to be able to move off the center x equals 0 to the left or to the right. We're not carving out another function, so there is actually no radius of convergence. Okay, so we say the radius of convergence is actually 0. 0 is the amount I'd move to the left and to the right of x equals 0. All right, so by the ratio test, the series diverges, and I'm going to put for absolute value of x, what I found up here, greater than 0. That's just a way of saying that it diverges when you move off the center. And consequently, and it converges only at its center. Okay, and so finally, so the radius of convergence, uppercase R represents the radius of convergence, is equal to 0. All right, and thinking about something else that we said, so what is the interval of convergence? Well, there is no interval of convergence, and I'm just going to let I and C represent interval of convergence. So there's no interval of convergence. All right, so this is all new. It might seem a little strange, so let's continue and look at some different power series to determine the radius of convergence for those. All right, for example 2, let's just go ahead and generate a few terms. It's not necessary for finding the radius of convergence. It's just good practice to generate some terms. Plus, once you get them out there, if you wanted to confirm at the end by using your graphing calculator to graph terms to see verify your radius of convergence and what you found, that's a good idea. All right, so if n equals 0, well, anything to the 0 power is going to be 1, so my first term is actually going to reduce down to just 3. Sometimes it's just good to see the structure, though. So all that's happening is that the power here is increasing. and that right here is just a plus. All right, and something else we can take from this is what is the center. We can see here that the center is going to be x equals 2. So that is a good thing to document. All right, when x is 2, if you wanted to take the graphical approach to see if you can kind of figure out what the radius of convergence would be, what you could do is graph this as y1. y2 would be these two terms. y3 in your calculator would be these three terms. y4 would be these four terms. And just kind of watch the progression of what's happening, the intersections of these graphs, to kind of get an idea of what the radius of convergence might be. All right, so to find the radius of convergence, let's use the ratio test. All right, everywhere you see n, replace it with n plus 1. I'm going to build a quotient here. Alright, a little bit of cleanup. The 3's will cancel. Quantity x minus 2 to the n will cancel. So this will all cancel with this, leaving just one of the x minus 2 terms. Okay, so now at this point, remember this is a limit in terms of n. There is no n in here. This is what we're going to do. I'm actually going to pull out x minus 2, leaving it in absolute value. Since the limit doesn't depend upon the variable x, I'll pull that whole thing out, and I'll leave it as limit as n goes to infinity, and what I'm going to have left in here is just 1. All right, well, what is this limit? And we'll take that answer and multiply it by the absolute value of x minus 2. Well, we see that that limit is just 1, so we're left with absolute value of x minus 2. Alright, so it's a little bit strange because remember we're in the ratio test right here, and with the ratio test, if we get a number that's less than 1, we know the series converges. If when we apply the ratio test we get a number that's bigger than 1, we know the series diverges. Well, we can see here that we didn't get a number, we just got another expression. So what we do is we want this thing to converge, and if we want it to converge by the ratio test, we force this to be less than 1. So all I did was add on a less than 1 here, since this is only in terms of x. Alright, so from this point right here, okay, we can see that there's no cleanup to do right here. I just have the expression x minus 2. I don't have a coefficient on x. I'm not dividing by anything. I wanted to isolate the expression in terms of x by itself here. And since it is that way right now, okay, we can say that the radius of convergence is actually just going to be 1. We want to stay within 1 unit of the center, x equals 2. Okay, so let's put this all together then. Okay, so by the ratio test, the series is going to converge as long as I allow this expression to be less than 1. It would diverge if it was greater than 1. All right, so therefore, the radius of convergence is 1. I have to stay within 1 unit of my x equals 2 center. Right, so what does that mean for the interval of convergence? Well, think about where the center is. The center is at x equals 2. So when you think about the center being at x equals 2, you can only go as far as 1 to the left and 1 unit to the right of x equals 2. Okay, so right now, to be within 1 unit of the center of x equals 2 means I can go as far left as 1 and as far right as 3. Okay, so you can kind of consider this the interval of convergence. And what I mean is kind of consider it when we get to the interval of convergence, which is on the next page, we have to test the endpoints, and you'll see what that looks like. because sometimes with the endpoints we can include them with brackets, and sometimes we have to exclude the endpoints, those x values, by using a parenthesis. So we haven't tested the endpoints yet. That'll be in the next on the next page. Okay, but for this particular power series, if I stay within 1 unit of x equals 2, then we can say that the power series converges. Okay, or graphically, if you take approach, the more terms you pick up to graph, you can see that there's a more overlapping or a growth of the function from 1 to 3. All right, for our third example of a radius, finding radius of convergence, you can see that the series is a little more complicated. So what I'm going to do is I'm going to generate a few terms off the video, and then I'll turn it back on and you'll just see that they're all there. So let me do that real quick. All right, so generating a few terms and doing a little bit of cleanup, you guys can see this expansion, and you might recognize it. We've already seen this one right here. Okay, we've seen this, I believe, is the sine function. So this power series represents the sine function. So if we kind of think about that before we find the answer to the radius of convergence, the more terms that we add, okay, the more of the sine function is going to grow. So actually the radius of convergence should be infinity. Okay? It should be all real numbers. Okay? The interval of convergence should be all real numbers. The radius of convergence should be equal to infinity. Meaning that I can travel as far to the left of x equals 0, the center, as I want, and as far to the right of x equals 0 as I want, because the more terms I pick up, I'm going to have more of the sine function. All right, well, let's go ahead over here and document the center. Okay, all these terms are going to intersect at x equals 0, and you can quickly see that if you let x be 0 in every single one of these terms, the output, the answer, the y value, whatever, is 0. So all these points are going to intersect at the origin. All right, so let's find the radius of convergence by using the ratio test. So I'm going to do the setup on it, and then I'll come back with you guys once it's all there. All right, so there it is. It was pretty intense. I don't know if you say intense, but got a lot of work to set it up. All right, so we have the setup here of the ratio test. Time to do some cleanup. You might notice that you're going to have to distribute the 2 here and the 2 down here first of all. So we'll do that cleanup. So this is going to be x raised to the 2n plus 2 plus 1 more. So x raised to the 2n plus 3. And then down here, if we distributed the 2, we're going to get 2n plus 2 plus 1 more. So this becomes the factorial 2n plus 3. Makes sense. It matches this exponent. Okay, and running out of room, I'm going to come down here. I think we can start canceling some things. Alright, so because we're doing the absolute value, neither of these matter here. They're both going to be positive at the end. Alright, we can see right up here that we have x to the 2n times x cubed, and this is x to the 2n times x to the first. So you could separate them, or you can just visualize what that would look like cleaned up. So on the top, I'm going to cancel x to the 2n, and I'm going to have the x cubed still remaining. And I'll cancel the x to the 2n and still have x to the first. So x cubed over x to the first, this x will cancel with one of those. So actually in the numerator, all I'm going to have is x squared. All right, so we're going to have to do some work with these factorials too. The bigger factorial would be this one right here, because I'm adding 3, whereas over here I'm just adding 1. Okay, so what I'm going to do is I'm going to take a couple of these numbers out here. So taking out whatever the number 2n plus 3 is, reduce 3 by 1, take out 2n plus 2, okay, reduce this by 1, and I'm going to have 2n plus 1, and I want to keep taking out numbers until I match this factorial so I can cancel. So then I'm left with 2n plus 1, and what I'm going to do is I'm going to put the factorial back on here so that I'm now able to cancel. Right, so 2n plus 1 will cancel with 2n plus 1 here. So my denominator is just the product of these two binomials. Alright, so that x squared could have scooted over a little bit, but that's okay. Alright, at this point we're ready to apply the limit situation. Well, it's only in terms of n, so I can pull the absolute value of x squared out front. In this case, absolute value isn't really necessary because the result of squaring x anyway is going to be positive, but we'll leave it on there. Okay, so at this point, applying the limit situation, the denominator would be super huge. So the value of this limit is actually going to go to 0. So when I multiply 0 by the absolute value of x squared, if I wanted to rewrite that, it would look like this. I get 0. Remember, we're applying the ratio test, and 0 is a number less than 1. So now we're ready to respond. So by the ratio test, the series converges for all x, no matter what x is. Okay, so therefore, the radius of convergence, okay, is going to actually be infinity. And from that, we can see that the interval of convergence would be all real numbers. I wouldn't have to test endpoints on this because I'm not going to test an infinity. The only time we're going to test endpoints is as if we got something like we did in example 2. So in this video, I tried to show 3 different situations that can occur as far as the radius of convergence is concerned. Either you're going to get the radius of convergence is 0, as in example 1. You're going to get a numeric value, as in example 2, and not that the radius always has to be 1 if it's not 0 or infinity. It just happened in that case to be that way. Or the third case is your radius of convergence would be infinity. Right, so in the next video, we'll find the interval of convergence, meaning we have to do all of this again, but in case we have to test endpoints, we will at that point.